Hi students, welcome back. This is a video on the two kinds of comparison tests. So there's two types of comparison tests in Calculus 2. There's the direct comparison test, which I have highlighted in red here. And then there's the limit comparison test, which is in blue. Okay, so for the direct comparison test, it says that if you have two series, sum of an and sum of bn, and if sum of bn converges and an is less than or equal to bn for all n, then sum of an converges. So what that's basically saying is, since bn is greater than or equal to an for every n, and bn converges, it should make sense that an can't go to infinity, since bn isn't going to infinity. Okay, so that one should kind of make sense in a way, because since an is always smaller than bn, less than or equal, and bn converges, an can't go to infinity, right? Because it's bounded above by bn, and bn converges. Now, on the other hand, if the sum of bn diverges, in other words, the sum of bn goes to infinity or negative infinity, and an is greater than or equal to bn for every n, then the sum of an diverges. So this one is kind of the whole thing in reverse. This is still considered part of the direct comparison test, but this is case 2. So it's saying that in this case, if an is larger than bn for every n, and we know that bn diverges, in other words, bn is going to go to infinity or negative infinity, then that means sum of an also has to diverge. And that should also kind of make sense, because if an is greater than or equal to bn and bn is going to infinity, it should make sense that an can't go to a finite number. It also has to go to infinity or negative infinity. So just roughly speaking, hopefully those things sort of make some intuitive sense to you. Okay, and then the third one is the limit comparison. For that one, if the limit as n goes to infinity of an over bn equals c for some positive real number c, then both series converge or both diverge. That one's called the limit comparison, because you're literally just taking the formula for an, dividing it by the formula for bn, and you're taking the limit as n goes to infinity of that ratio. So it's a little bit like the ratio test, but it's actually a limit here. Okay? Alright, so we're going to be starting with the direct comparison test, so that hopefully we can see each of these two cases. And then later on we'll do an example of the limit comparison test. Okay, so let's jump into an example. Okay, example. Use the comparison test. Use the comparison test to determine if the following series converges or diverges. Okay, so use the comparison test to determine if the following series converges or diverges. So, a lot of words there. And they're not saying which comparison test to use, but we already know there's two of them, right? The two of them are that we just talked about are going to be direct comparison, and that's what we're going to be doing on some of the earlier problems, and then limit comparison is the other one we can use there. But here they're just calling it the comparison test. By that they mean it's going to be one of these three cases here. Okay, it's either going to be one of the first two for the direct comparison, or it's going to be the third one for the limit comparison. Okay, and they're not asking us for what it converges or diverges to, they're just asking whether it converges or diverges. And for our first example, example number 1, we're going to be looking at the sum from n equals 1 to infinity of 1 over 3n squared plus 25. the sum from n equals 1 to infinity of 1 over 3n squared plus 25. All right, so the basic idea here is with this one and this one in your homework, you might have different numbers, but it'll be the same idea. What you want to do is you want to compare this to something else. So we're going to call this right here, when I'm circling in red, that's going to be our an. Okay, and for this one, we're going to go ahead and use the direct comparison test. So we want to find another series Bn such that an is less than or equal to Bn, or an is greater than or equal to Bn. So we need to find one of those, we need to find another series, sum of Bn, such that one of these is true. That way we can use the information to determine whether it converges or diverges. Okay, so the hard part is thinking of the Bn. So now what I'm going to do here is kind of what they do on my math lab, which is we're going to notice something here. We're going to notice that if we look at, say, n squared, we know that n squared is less than or equal to 3n squared, right? Because if you multiply a positive number by 3, that has to be greater than or equal to n squared. And then I'm going to kind of work with this. So what I want to get to is I want to get to an. I want to get it in the form where I'm comparing something to an. So I need to get it as 1 over 3n squared plus 25. So far I already know this. Well, if I add 25 to 3n squared, because 25 is a positive number, I can add 25 right here. So 3n squared is less than or equal to 3n squared plus 25. And in fact, because we're adding 25, it's not just less than or equal, it's actually less than. Okay, so you might be kind of confused, well, where is this coming from? And why did I choose n squared? Well, the reason I chose n squared is if we can get it in the format where we have this compared to 1 over n squared, then we'll be able to determine whether it converges or diverges, because 1 over n squared is going to be a p-series. Okay, so anyway, what we have so far is n squared is less than 3n squared plus 25. Right, that should be very clear, because n squared is a positive number, so 3n squared is greater than or equal to it, and then 3n squared plus 25 is greater than that. But what we want is actually 1 over 3n squared plus 25. So how do we get that? How do we get this out of what I have written here? The answer is we're going to take the reciprocal of each side. In other words, here we're going to divide both sides. Oh my gosh, what did I just open? We're going to divide both sides by both 3n squared plus 25. Okay, so I divide both sides by 3n squared plus 25. So on the right side, the 3n squared plus 25's cancel. So I get n squared over 3n squared plus 25 is less than 1. Okay, and then I want to get it in a format where I can compare this 1 over 3n squared plus 25 to the n squared. So now I'm going to divide both sides by n squared. Okay, in other words, I'm going to multiply both sides by 1 over n squared. Okay, so what's that going to give me? Well, now I'm going to have the original series that we started with, at least the formula for it. We have 1 over 3n squared plus 25 is less than 1 over n squared. And it's not quite this hard on my math lab because they have multiple choices, and you're going to be able to look at the different choices and choose one that makes sense. So you're not actually going to have to come up with all this on your own like I am. So I know this seems very difficult, and it is difficult. I'm not going to lie, it's difficult. But you're not going to necessarily have to come up with all this because you're just going to have 4 multiple choices. And then only one of them is going to make sense. So you click on the one that makes sense. But they already have them written out for you, whereas I'm having to do it from scratch here. So what this is telling us is, remember, this is the formula for our original an. So here our an is going to be 1 over 3n squared plus 25. And then we can see that our bn is going to be 1 over n squared. Okay, and if an is less than bn, that's the same as saying an is less than or equal to bn, because if it's less than, it's also less than or equal. Same thing. So what we can do is we can go back up to our direct comparison test. So the direct comparison test says if sum of bn converges and an is less than or equal to bn for every n, then sum of an converges. So here, like I was saying, this bn is something that we can determine quite easily. So if we look at sum of bn is going to be the sum from n equals 1 to infinity of 1 over n squared. And like I said before, this is a p-series. So if you go to your formula sheet on page 3, under p-series, if you have the sum from n equals 1 to infinity of 1 over n to the p, let me zoom in. The sum from n equals 1 to infinity of 1 over n to the p, that's a p-series, it converges if p is greater than 1, and it diverges if p is less than or equal to 1. So here we can see that p is actually 2, so this is going to converge. Okay, so this is a p-series. P equals 2, which is greater than 1, so it converges. And then because bn converges and an is less than or equal to bn, since this one converges, that means this one can't diverge, so this one also has to converge. So hopefully that makes sense. Okay, so sum of bn converges, which means an also converges. Okay, so thus sum of an from n equals 1 to infinity converges. And that's by the direct comparison. Okay. So that was actually the first one that I showed you up above. Okay, cool. So these take a long time to do, so I'm not going to be able to do every single type of problem on your homework, but I'm going to try to give you the most important ones, and then you can experiment a little bit on your own on the other ones. Okay, so let's see another example. Okay, so that one we just did was example number 1. And we still have these instructions. So use the comparison test to determine if the following series converges or diverges. And when they say comparison test, it means either the direct comparison or it means the limit comparison test. So for number 2, we have the sum from n equals 1 to infinity of cosine squared of n over n to the 9/2. Okay, the sum from n equals 1 to infinity of cosine squared of n over n to the 9/2. So something to keep in mind whenever you have a trig function like sine or cosine, remember that sine and cosine are between -1 and +1. Okay, so this is something just to recall from your pre-calculus class. -1 is less than or equal to cosine of n, which is less than or equal to +1. And even though our letter is n, it's just like cosine of x. It's just n is a natural number. Okay, but cosine is still between -1 and +1. And if we square it, if we square that, if I do cosine squared of n, that's also going to be, because it's squared, it can't be negative, but you square something, if you square everything here, cosine squared of n is also going to be less than or equal to 1. It can't be negative because when you square a negative, it becomes positive, but if you square 1, you still get 1. So cosine squared of n is less than or equal to 1. So the reason why that's important, the reason why I wrote that, is we can actually rewrite this as, we can write our bn as 1 over n to the 9/2, because cosine squared of n is less than or equal to 1. Okay, so let's see how that's going to work out. So since cosine squared of n is less than or equal to 1, now we do the magic step, which is basically, we notice that to get from this thing here, the cosine squared of n, to this, all we have to do is divide both sides of this inequality by n to the 9/2. So that's actually what I'm going to do there. Okay, so I'm going to divide both sides by n to the 9/2. Okay, and then once again, now we have our bn. Okay, so we have cosine squared of n over n to the 9/2. That's actually our an. This one right here is our an. And then this is less than or equal to 1 over n to the 9/2. And because it's less than or equal, this other one, the 1 over n to the 9/2, this one's going to be our bn. Okay, and then by the direct comparison test, since an is less than or equal to bn for all n, if we can determine whether bn converges, if sum of bn converges, then that means sum of an converges. Well, let's take a look at sum of bn. Sum of bn from n equals 1 to infinity equals the sum from n equals 1 to infinity of 1 over n to the 9/2 Okay, and that's also a p-series. That's another p-series. It's a p-series where p is the exponent. So p equals 9/2. And once again, just like the last problem, 9/2 is greater than 1. So that means it converges. So that means the sum of bn converges. And then by the direct comparison test, because an is less than or equal to bn, that means I'll just put an arrow here. Then sum of an converges. and that's by the direct comparison test. It's actually pretty similar to the last problem we did. It just had that bit with cosine, so that's why I wanted to explain that to you. And remember that sine, if you end up with sine on your homework, sine is also between -1 and +1. So you can do the same thing if you had sine squared of n, so that would also work. Okay, so let's take a look at example number 3. So for example number 3, we have a little bit more complicated formula. So for this one, it's the sum from n equals 1 to infinity of n minus 2 over n cubed plus 2n squared plus 3. Okay, the sum from n equals 1 to infinity of n minus 2 all over n cubed plus 2n squared plus 3. All right, and here they give us a hint. Okay, so they give us a hint on some of these problems. For this one, the hint that they give us on your homework is we need to use the limit comparison test with sum from n equals 1 to infinity of 1 over n squared. Okay, so we're going to use limit comparison. Limit comparison with sum from n equals 1 to infinity of 1 over n squared. And with these, they're pretty nice about it because they actually give you a hint what you're supposed to use for your limit comparison, and then we go with that. Okay, so what was the limit comparison? Well, if I scroll all the way back up here, that was actually the third case. So in blue here, the limit comparison says, if the limit as n goes to infinity of an over bn equals c for some positive real number c, then both series converge or both series diverge. So if one of them converges, the other one converges. If one of them diverges, the other one diverges, as long as their limit, the limit of their ratio, equals c. Okay, so let's see how we can use that here. So first of all, we label our original function, our original expression here as an, and then our bn is going to be this 1 over n squared. Okay, and since they told us to use the limit comparison, that means we're going to be doing the limit as n goes to infinity of an over bn. Okay, so that's going to be the limit as n goes to infinity. Well, an was kind of complicated. An was actually all of this. So it's going to be n minus 2 over n cubed plus 2n squared plus 3. Okay, so over n cubed plus 2n squared plus 3. And then this is going to be over bn, which we said was 1 over n squared. Okay, so this is going to be over 1 over n squared. So if you're dividing by 1 over n squared, that's the same as multiplying by the reciprocal. Okay, so if we divide by 1 over n squared, we can flip it over and multiply by n squared on the top. And I know right now it doesn't seem like this is going to help us very much, but in a second you're going to see why it's helpful. Okay, so we're going to get the limit as n goes to infinity. After we flip that over, we're going to have n squared times the quantity n minus 2 all over n cubed plus 2n squared plus 3. So on the top here, if we go ahead and distribute that n squared to each of those terms, we're going to get n cubed minus 2n squared. Okay. So in the numerator we have n cubed minus 2n squared. Alright, and if you remember how to evaluate an infinite limit, the basic idea is if you're evaluating an infinite limit and you have a rational expression, in other words, you have a fraction like this, basically you divide the top and the bottom by the largest power in the denominator. Okay, so divide top and bottom by largest power on the bottom. Okay, so in other words, divide the numerator and the denominator by the largest power in the denominator. Okay, so here the largest power in the denominator we can see is actually 3. Okay, my mouse is messing. So we divide the top and the bottom by the largest power on the bottom, which is n cubed. Okay, so remember, dividing is the same as multiplying by the reciprocal. So we're going to multiply the top and the bottom by 1 over n cubed. Okay, multiply the top and the bottom by 1 over n cubed. And then if we distribute on the top, we're going to get n cubed times 1 over n cubed is 1. Okay, so we have 1 minus 2n squared over n cubed is going to be minus 2 over n. So we have 1 minus 2 over n on the top. And then on the bottom we have 1 plus 2 over n plus 3 over n cubed. And this is an infinite limit, so we're taking the limit as n goes to infinity. Now remember, if you take the limit as n goes to infinity, and you have a fraction where you just have the variable in the denominator, and you don't have a variable on the top, that's always going to go to 0. Okay? So this negative 2 over n, as n goes to infinity, the denominator becomes infinitely large, but the numerator stays fixed, which means that the whole thing goes to 0. So this one goes to 0, the 2 over n on the bottom goes to 0, and the 3 over n cubed also goes to 0. So our limit is actually going to be the limit as n approaches infinity of 1, which is just 1. Okay, and then if we go back to the limit comparison test, we're going to be able to see for the limit comparison test, they said that if the limit equals a constant, so a positive real number c, then either both series converge or both series diverge. So going back down here, going back down here, this is our c. This is our c. So c equals 1, which is greater than 0. Remember, they said it had to be a positive real number. So by limit comparison, by the limit comparison test, we know that both series diverge or both series converge. Okay, so both series converge or both series diverge, or both series diverge. Okay, but the series that we had were we had 1 over n squared, and then we had this big one, n minus 2 over n cubed plus 2n squared plus 3. But for the 1 over n squared for our Bn, we know that that one is once again a p-series. Okay? So what I'm saying is sum of Bn here from n equals 1 to infinity equals the sum from n equals 1 to infinity of 1 over n squared, which is once again a p-series. Okay, so this is a p-series, and we can see that our exponent in our denominator is p equals 2, which is greater than 1. So that means the sum of Bn converges. Okay, the sum of Bn converges, but then by the limit comparison test, either both series converge or both series diverge. So since sum of Bn converges, that means we have sum of An also converges. Okay. So since the sum of Bn converges, that means the sum of An also converges. So that's how the limit comparison test works. After you take the limit, as long as it's a positive real number, either both of them are going to converge or both of them are going to diverge. So if you can figure out what the sum of Bn does, then you know that the sum of An does the same thing. And in this case, because sum of Bn converges, sum of An also converges. Pretty cool, huh? So that's the limit comparison test. Alright, so we finished example number 3, and then there's just a few more I want to do to prepare you for your homework. Okay, so let's take a look at example number 4. Okay, example number 4. So this one looks a lot like an earlier problem. This one is the sum from n equals 1 to infinity of sine squared of n over 2 to the n. Okay, the sum from n equals 1 to infinity of sine squared of n over 2 to the n. So for this one, we want to use the direct comparison test because it's similar to an earlier problem that we did, and for that one we also use the direct comparison test. Okay, so what we're going to compare this one to is 2 to the n. Well, actually 1 over 2 to the n is what we want to compare it to. But, just like before on the earlier problem with cosine, realize that sine is greater than or equal to negative 1 and less than or equal to positive 1. And that's true for any sine function. So sine of n is greater than or equal to negative 1 and less than or equal to positive 1. Okay, and then if you square it, it's still going to be less than or equal to 1. So we have sine squared of n is less than or equal to 1. Okay, and then if we go ahead and divide both sides by 2 to the n, we're going to get this same expression here. So that'll be our an, and it'll be less than or equal to our bn. Okay, so we divide both sides by 2 to the n. Okay, so that brings us to a format where we can use the direct comparison. So we have sine squared of n over 2 to the n is less than or equal to 1 over 2 to the n. And this right here is a setup for us to do direct comparison. Okay, so I'm going to label the first function as our a sub n, and I'm going to label the second function as b sub n. Okay? And since an is less than or equal to bn for all n, we can use the direct comparison test. Okay, so to use that, we need to show that Bn either converges or diverges. In fact, we need to show that it converges in order to show that An also converges. Okay, so what we got here is we got the sum of Bn is actually equal to the sum from n equals 1 to infinity of 1 over 2 to the n. Alright, and I don't know if you remember this, but this is actually a geometric series. Okay, this is the same as the sum from n equals 1 to infinity of 1/2 raised to the nth power. So this is actually in the format the sum of a times r to the n. Here we can see a equals 1, and then r equals 1/2. And remember, with geometric series, if r is less than 1, then it's going to, the series is going to converge. So if we go up here on our formula sheet on the third page, and we scroll up to geometric series on the third page, the sum of a times r to the n, or sum of a times r to the n minus 1, it converges if the absolute value of r is less than 1. Okay? And we have that here. Since r equals 1/2, that means the absolute value of r is less than 1. Okay, so since the absolute value of r is less than 1, that means it converges. It's a geometric series. Okay, so this is a geometric series, and this converges. So that means the sum of Bn converges. So then, using our direct comparison test, since An is less than or equal to Bn, and sum of Bn converges, by the direct comparison, I'll just write dc, we get sum of An also converges. Okay, so this is very similar to an earlier problem we did. It's just the earlier problem had a p-series, whereas this one has a geometric series. But the sine squared of n was very similar to the cosine squared of n. So hopefully that one wasn't too bad. Pretty similar to the earlier problem. Okay, so let's keep going here. So the one we just did was example number 4. So let's jump in to example number 5. Now this one's a little bit of a trick question. Okay, so for this one they say, use the appropriate test. Use the appropriate test to determine whether the series converges or diverges. Use the appropriate test to determine whether the series converges or diverges. So, maybe instead of calling this example number 5, I'll just call this a new example, since it has new instructions. So, yeah, that's what I'm going to do. Okay. Sorry, let's just call this a new example. Since it has new instructions, we'll make this a new example. Use the appropriate test to determine whether the series converges or diverges. Notice here they're not saying you have to use the limit comparison test or the direct comparison test. They're just saying use the appropriate test. That means you can use any test that you want. Right? So the appropriate test just means you can use whatever test that you can think of that will actually allow you to determine whether the series converges or diverges. So this one opens up to some of the older tests that we've learned in previous videos. Okay, and for number one, for example number one of our new example, we're going to have the sum from n equals 1 to infinity of 2n over 5n minus 3. Okay, the sum from n equals 1 to infinity of 2n over 5n minus 3. So what we want to do with this one is, because it's pretty simple, and it would be easy to do an infinite limit for, I think the first test that we want to think about using here would be the nth term test for divergence. Okay, so that's the one I'm going to use here. So let's try the nth term test. Nth term. So the time you want to use an nth term test is in a situation like this, where it's very easy to calculate the infinite limit, because on the top you have a 2n, on the bottom you have a 5n minus 3. So by the nth term test, if we do the limit as n goes to infinity of 2n over 5n minus 3, that's actually going to be very easy to calculate. And remember, for the nth term test, if we go back to our formula sheet, the nth term test says that the sum of an diverges if the limit as n goes to infinity of a sub n is not equal to 0. So if it's any number besides 0, or if it's infinity or negative infinity, that means sum of an diverges. And the reason I'm using this one here is, look how easy it is to calculate this limit. All we have to do is multiply the top and the bottom by 1 over the largest power on the bottom. So we're going to multiply the top and the bottom by 1 over n. Okay, so on the top, we're going to have 2n over n, which is 2. And then on the bottom, we're going to have 5 minus 3 over n. Okay, and we're taking the limit as n goes to infinity of 2 over 5 minus 3 over n. And remember, with these infinite limits, you always multiply the top and the bottom by 1 over the largest power in the denominator. In other words, you divide the top and the bottom by the largest power on the bottom. Okay, now remember, with the nth term test, after we calculate this limit, if the limit is any number besides 0, then we know that the series diverges. So like here, the negative 3 over n, as n goes to infinity, this is going to go to 0. Okay, so our limit is actually going to be 2 over 5. Okay, and 2 over 5 is not equal to 0. And if you don't remember the nth term test, make sure you go back to my earlier video from a previous week where I talk about the nth term test for divergence. Okay, so since we get our limit is 2/5, which is not equal to 0, that's the limit as n goes to infinity of a sub n equals 2/5, which is not equal to 0. The nth term test says that sum of a sub n diverges. Okay. Because remember, the nth term test says that if your limit, your infinite limit, is any number besides 0, or if it's infinity or negative infinity, then that means your series diverges. The main reason I did this example is sometimes when you do these kinds of problems where they leave it open-ended, it's hard to think of which test to use, so that's why I'm giving you this example here. Alright, cool. So that was example number 1 of our new example. Okay, so let's do example number 2. So for example number 2, we have the sum from n equals 1 to infinity of 2n plus 7 over n times n plus 1 times n plus 2. Okay, the sum from n equals 1 to infinity of 2n plus 7 all over n times n plus 1 times n plus 2. So once again, these are going to be multiple choice on my math lab. So you want to just look at the different choices they have, and then look at the ones that make the most sense, and then try to do some math to make sure that you have the math to back that up. So like with this one, I think what I'm going to do is the comparison test. And you know, you can either do the limit comparison test or you can do the direct comparison test. But here I think I'd like to do the direct comparison test. Okay, so direct comparison. So for that one, basically what we need to do is we need to compare this one to something that's simpler. So something like a p-series. So I want to compare this to a p-series. So what I'm going to do is I'm going to start out by actually simplifying this a little bit. So if I go ahead and multiply this all out, on the bottom, if I go ahead and, oops, I gotta stop clicking that button with my pen. Sorry about that. So on the bottom, I can go ahead and I can multiply this part out with FOIL. And the reason I'm bothering to do FOIL and multiply everything out is to use the direct comparison test. It needs to be written in a way where we can actually compare it to something. So, so what we're going to have here is we're going to have the sum from n equals 1 to infinity of 2n plus 7 over n times n squared plus 2n plus n, so that's plus 3n plus 2. And I'm multiplying this all out. So while I'm at it, why don't I go ahead and distribute the n here. Okay, so I'm going to distribute this n to every single term on the bottom. Okay, so that's going to give us the sum from n equals 1 to infinity of 2n plus 7 over n cubed plus 3n squared plus 2n. And then there's a trick with this problem. The whole reason I'm doing this problem on the video here is there's a trick with it that a lot of people probably wouldn't think of. So before we go ahead and actually do the direct comparison test, I'm noticing something here. I'm noticing that every term on the bottom has an n, which would mean that if I divided the top and the bottom by n, I would get a lot simpler expression to work with here. Okay, so I'm going to actually multiply the numerator and the denominator by 1 over n. And that's the trick here. How would you even think of doing that? Well, it can be difficult. But I'm going to show you why it works. Okay, so on the top we have 2 plus 7 over n. And then on the bottom we have n squared plus 3n plus 2. Okay, so then let's work on this. So let's start with the n squared plus 3n plus 2. Since n is going from 1 to infinity, we can compare all this to 2 over n squared is what I want to compare it to. So what I'm going to say is I want to say that this whole thing is less than or equal to 2 over n squared. So I want to say 2 plus 7 over n all over n squared plus 3n plus 2. I want to say this is less than or equal to 2 over n squared. Now the reason that I'm trying to say this is if you look at 2 over n squared, that's actually just a p-series. Okay? And so I'm trying to compare this to a p-series. But I actually need to show this. Okay? I need to show this. So why is this true? Well, first of all, 2 plus 7 over n isn't going to make a big difference as n goes to infinity. And then in the denominator, we actually have an n squared plus 2n plus 2. Sorry, n squared plus 3n plus 2. So how do we show this? Well, first of all, we know that n squared is less than or equal to n squared plus 3n plus 2. Right? We already know that because n squared is a positive number, and that's less than or equal to n squared plus 3 times n. Remember, n is going from 1 to infinity, so n is a positive number, plus 2. Because this 3n plus 2 has to be a positive number. And what else do we know? Well, if we go ahead and divide both sides of this by the reciprocal, that means we're going to have 1 over n squared plus 3n plus 2 is less than or equal to 1 over n squared. And then how do we get this top part? How do we get the 2 plus 7 over n is less than or equal to 2? Well, what I would say is, since this denominator is actually larger than that denominator, I would say that here, if we multiply both sides by 2, if I multiply both sides of this equation by 2, I'm going to get 2 over n squared plus 3n plus 2 is less than or equal to 2 over n squared. And then if I add in a 7 over n here, the denominator is still larger than this denominator, so the expression is still going to be true. Okay, and why is that true? Well, if I add 7 over n over here, that might not be true, but if I just added it on the left side, it's still going to be less than or equal. Okay, and I don't really want to go into the details of that, but we kind of have shown that this is true. Okay, so since we've shown that that is true, now we know that our an is less than or equal to our bn. Okay, so we have an is less than or equal to bn. Okay, and then with bn, we know that the sum of bn is equal to the sum of 2 over n squared, which is, you know, you can just factor out the 2. So we have 2 times the sum of 1 over n squared from n equals 1 to infinity. And once again, that bn is a p-series. Okay, so this is a p-series, and the exponent is 2, so p equals 2, and 2 is greater than 1, so that means it converges. And if it converges, that means it goes to a finite number. And 2 times a finite number is still a finite number. So that means 2 times a p-series, or any number times a p-series, still converges. Okay, so that means our sum of b sub n converges. And then by the direct comparison test, now we know that the sum of a sub n also converges. And we know that because we said that an is less than or equal to bn for all n. Okay. An is less than or equal to bn for all n. Pretty cool, huh? And you know, there's lots of different ways of doing these problems. My idea was to multiply the top and the bottom by 1 over n. You didn't have to do that, though. You might have been able to leave it as n cubed plus 3n squared plus 2n on the bottom, and then work with that. But the way I did it worked fine as well. So there's different ways of doing it. But regardless of which way you do it, you should be able to find out that sum of an converges here. Okay? Cool. So there's just one more that I need to do here. Okay, so our last example for this lecture, I know it's getting to be a long lecture, we're almost to an hour now. Our last example, example number 3, once again says use any test, any appropriate test to determine whether the series converges or diverges. And for this one, we have an unusual function. We actually have the sum from n equals 1 to infinity of parentheses n over 4n plus 9, parentheses raised to the nth power. Okay, so the sum from n equals 1 to infinity of the quantity n over 4n plus 9, quantity to the nth power. And for this one, we want to actually compare this to another series. And we're going to use the comparison test for this one. So which comparison test do we want to use here? Well, we can either use the limit comparison test or the direct comparison test. I think I'm going to use, I'm going to use the direct comparison test. You could also use the limit comparison test, but that might get a little messy. So I think I'm going to use direct comparison. Okay, so for the direct comparison test, what are we going to do here? Well, we need to create a new series, and we need it to actually be something that we can compare to this one. So let's start with our original series. We're going to call this original series a sub n. So this right here is our a sub n. And now we need another series b sub n, so that we need to find one where an is less than or equal to bn for all n. So the thing is here, if you just look at the n over 4n plus 9, if we look at n over 4n plus 9, if I go ahead and multiply the top and the bottom by 1 over n, if I multiply the top and the bottom by 1 over n, this is going to give me 1 over 4 plus 9 over n. Okay, and 1 over 4 plus 9 over n is going to be less than or equal to 1/4. Now, how on earth did I decide that that's less than or equal to 1/4? Well, because 9 over n is actually going to be a positive number, because n goes from 1 to infinity, n is always a positive number, so 9 over n is also a positive number. That means this denominator is going to be bigger than 4, which means 1 over that is going to be less than or equal to 1 over 4. So this one's kind of tricky. This is actually probably the trickiest problem on your whole homework because of this part right here. And again, the reason this is true is because this denominator is bigger than that denominator. So then when you do 1 over, that means this one has to be less than or equal to that one. So this right here, this is true because we know that 4 is greater than or, 4 is less than or equal to 4 plus 9 over n. So if you divide both sides by 4 plus 9 over n, and you divide both sides by 4, in other words, you take the reciprocal, just like we did on the earlier problems, then that means you're going to have 1 over 4 plus 9 over n is less than or equal to 1/4. Okay, so you might be wondering, well, why am I doing all this? And what does this accomplish? Well, since we know that this one here is less than or equal to 1/4 now, so now we have, what we have so far is we have n over 4n plus 9 is less than or equal to 1/4. Then what we can do with that is if we raise both sides to the nth power. Okay, so if I raise both sides to the nth power, I'm allowed to do that to both sides of the inequality, and that's not going to change anything. The inequality is still going to be true. Then we're going to discover we have our original function, n over 4n plus 9 raised to the nth power on the left side. And then on the right side, if I go ahead and I distribute that n to the numerator and the denominator, then on the right side I'm going to have 1 over 4 to the n. Or actually, since that is not going to be a p-series, why don't we just leave it as 1/4 to the n? That's probably would be better. Okay, so we'll just leave that as 1/4 to the n. That's not a p-series. That one's going to end up being a geometric series, so there's no point in distributing the n to the numerator and the denominator's exponents. Okay. All right, so then what do we do from here? So for this one, remember this on the left side, this is actually our a sub n. This is our a sub n. And then on the right side, because it's less than or equal, we're going to call this one on the right side the b sub n. So this one right here is going to be our b sub n. And so we have a sub n is less than or equal to b sub n. Okay, this original one was our a sub n. It's less than or equal to b sub n, which means we can use the direct comparison test, which is what I was going for. Okay, so now we just need to show that the sum of b sub n converges. So for the sum of b sub n, that's going to be the sum from n equals 1 to infinity of 1/4 to the n. And we can see that this is a geometric series because it's in the form, this is in the form sum of a times r to the n, which is geometric. Okay, so here we can see that a equals 1 and r equals 1/4. And since 1/4 is actually less than 1, absolute value of r equals the absolute value of 1/4, which is 1/4, and that's less than 1. That means the geometric series converges. So that means geometric series converges. And here that's the geometric series sum of b sub n converges. But then by the direct comparison test, since a sub n is less than or equal to b sub n, that means sum of a sub n also converges. Okay, so DC, standing for direct comparison, implies that the sum of a sub n also converges. So DC stands for direct comparison. I'm just too lazy to write it. Okay, so hopefully you'll be set for all your homework from this section now. I know this stuff is hard, but I'm hoping my video will help with that. So thanks for watching, and we got it done in a little bit more than an hour. Okay, have a good day.